I'm going to prove to you that pi equals 4. And every single step is going to look completely fine. That's the whole trick. There's no moment where I divide by 0, no sneaky algebra, nothing you can point at and go, aha, there it is. It all looks airtight. So here's what I want from you. Watch the screen, not me, and try to catch the exact second it goes wrong, because it does go wrong. Pi is not 4, it's about 3.14. You've known that since school. But knowing the answer is different from knowing where the argument breaks. I got this wrong the first time I saw it. I stared at it for a solid 10 minutes, convinced the picture was just correct and math had betrayed me. It hadn't. The picture is lying very politely in a way that's genuinely hard to spot. Keep your eye on one blue square in a minute. That square is the whole con. Let's build it. Start with a circle. Let's say its diameter is exactly 1. That's the distance straight across through the middle. And here's the only fact about pi you need for the whole video. Pi is the circle's perimeter divided by its diameter. That's it. That's the definition. So if the diameter is 1, then the perimeter, the distance all the way around, is pi, roughly 3.14. We want to measure that curvy distance around. Curves are annoying to measure, though. Straight lines are easy, curves are not. So we're going to do the thing every calculus trick does. We approximate the curve with straight stuff, and we make the straight stuff finer and finer until it hugs the curve. Now watch. Draw a square around the circle so the circle fits snugly inside, touching all 4 sides. That square has a side length of 1, same as the diameter, 4 sides, each length 1, so the square's perimeter is 4. Hold on to that 4. The square is on the outside, the circle is on the inside, and we're about to squeeze one into the other. Here's the move. The square is too big, its corners stick way out past the circle. So let's push the corners in, take each corner of the square and fold it inward until it just touches the circle. You end up with a blockier shape, kind of like a square with the corners bitten off. It hugs the circle a lot tighter now. Looks better already. But here's the thing I need you to notice, and this is the seed of the entire trick. When you fold a corner in, you replace one bent path with 2 shorter segments that go the same net distance. The little notch you cut out, the horizontal bit and the vertical bit, together they still cover the exact same width and the exact same height as the corner did. So the total length of the outline did not change. It's still 4. You made the shape smaller, you made it hug tighter, and the perimeter stayed exactly 4. That's not a rounding thing, it's exact. Fold a corner, length stays 4 every time. So we do it again. Every place the shape still pokes out past the circle, fold that corner in until it touches. Now there are more corners, more notches, more little steps. And again, every fold keeps the total length the same, 4. Do it again and again. Each round, the staircase gets finer, the steps get tinier, the shape wraps the circle more and more snugly. Watch it happen. After a few rounds, the jagged outline is basically sitting right on top of the circle. You almost can't see blue underneath anymore. It looks like the circle. It's practically touching every point of the circle. And the perimeter of this thing hugging the circle so tightly is still 4. It has been 4 this entire time, and it will be 4 forever, no matter how many times we fold. So the shape approaches the circle, and its length is stuck at 4. Feels like the conclusion writes itself, right? So here's the argument, laid out clean. The staircase shape gets closer and closer to the circle, as close as you want. Pick any tiny distance, and after enough folds, every point of the staircase is within that distance of the circle. Mathematicians would say the staircase converges to the circle. Meanwhile, the length of the staircase is 4, 4, 4, 4 forever. It never budges. So if the shapes are becoming the circle, their lengths should become the circle's length. The lengths are all 4. Therefore, the circle's perimeter is 4, and the circle's perimeter is pi. So pi equals 4. There it is. Every step felt reasonable. The shapes really do close in on the circle. That part is completely true. The lengths really are all exactly 4. That part is true too. And yet the conclusion is garbage because pi is not 4. So one of those reasonable steps is quietly a lie, not a math error. A hidden assumption. Take a second. Which one do you not trust? Here's the lie. It's the step that feels the most obviously true. The shapes get close to the circle, so their lengths get close to the circle's length. That sentence is just false, and I know it doesn't feel false. That's why this thing has fooled people for 100 years. Two shapes can be as close together as you like, sitting right on top of each other, and still have wildly different lengths. Closeness of the shapes does not force closeness of the lengths. Let me say it the blunt way. Length is not continuous. You can sneak length in through wrinkles that are too small to see. The staircase looks like the circle, but it's secretly still 4 units of path crammed into that thin band. All the length hiding in a zillion tiny right angles that never smooth out. They just get smaller. They never go away. And that's the difference between looking like the circle and being the circle. Let me convince you the wrinkles never leave. When you zoom in on a real circle, it looks flatter and flatter. Curves do that. They straighten out up close. That's the whole idea behind a tangent line. But the staircase does the opposite. Zoom in on the staircase and it does not smooth out. You just see the same staircase, smaller, more little steps, same right angles, same up, down, up, down. Every step is a corner where the path goes straight up, then straight across. And here's the number that matters. On each tiny step, you walk up and then across, but the circle would just cut diagonally. The staircase always walks the two legs of a little triangle, while the circle walks the hypotenuse, and the legs are always longer than the hypotenuse. Always. That extra length per step is small, but there are more and more steps, and it exactly balances out. The total wasted length stays constant. That's why it's stuck at 4. The waist never shrinks, it just spreads into more smaller wrinkles. Now here's what messes people up, and it messed me up. Area works fine. If instead of perimeter you measured the area inside the staircase, that number does converge to the area of the circle correctly. So why does area behave and length misbehave? Because area doesn't care about wrinkles. A wrinkly boundary can only trap a thin sliver of extra area, and those slivers genuinely shrink to nothing as the steps get finer. The little triangles we cut, their area goes to 0. But their perimeter, the length along their edges, does not. Area is forgiving. It measures how much stuff is roughly inside, and small wiggles on the edge barely change that. Length is fussy. It follows the boundary step for step, so every wiggle costs you, and a boundary can wiggle infinitely much while staying in an infinitely thin band. So the same sequence of shapes gives you the right area and the wrong perimeter at the same time from the same picture. That still kind of delights me. Let's make the loophole precise because there's a real and beautiful idea hiding under the trick. When we said the staircase converges to the circle, we meant the points get close. Every point on the staircase is near a point on the circle. That's called pointwise or uniform closeness, and it's true here. But arc length doesn't only depend on where the points are, it depends on the direction the curve is heading at each moment. It depends on the slope, the tangent, and the staircase's direction is insane. At every step, it's pointing straight up, then instantly straight across, up, across, up, across. It never once points along the circle. The circle's tangent turns smoothly. The staircase's tangent slams between vertical and horizontal forever. So the positions match, but the directions never do. And length is built from directions. That's the real theorem. To get length to converge, you need the tangents to converge, not just the points. The staircase fails that spectacularly, and it fails it at every scale. So how do you actually approximate a circle's length without lying? You use straight pieces, but you let them point along the circle. Instead of horizontal and vertical steps, use chords, little straight line segments connecting points on the circle itself, like a stretched rubber band pinned at spots around the rim. A hexagon inside the circle, then a 12-sided polygon, then 24 sides. Each one is straight-edged, easy to measure, and each edge actually leans along the curve. Now zoom in. These segments do flatten toward the circle. Their directions do line up with the tangent as you add more sides. And their total length climbs. 3, then 3.1, then 3.13, creeping up toward pi from below. This is literally what Archimedes did over 2,000 years ago, squeezing pi between polygons. Same spirit as the staircase, tile the curve with straight stuff, but the chords point the right way so their length tells the truth. The staircase looked closer to the circle and lied. The polygon looks rougher and is honest. That inversion is my favorite part. You might think this is a cute paradox that only lives on circles. It's not. This exact trap shows up anywhere you measure the length of a boundary. Coastlines are the famous one. Measure a coastline with a big ruler and you get one number. Measure it with a tiny ruler that follows every little inlet and the number grows, and it keeps growing because the wrinkles never stop. That's not measurement error. That's the same staircase problem wearing a geography hat. It's the seed of fractal dimension. It also bites people writing physics simulations and graphics code, where you approximate a smooth path with a jagged mesh and quietly get the perimeter wrong, even though the picture looks perfect. And it's why in real calculus, arc length has that scary formula with a square root and a derivative in it. That derivative is there on purpose. It's the tangent. The formula is specifically built to track the direction of the curve, because the staircase taught everyone the hard way that positions alone will lie to you. So the fix is basically don't trust a shape just because it looks like another shape. Looking alike is about position, length is about direction, and two curves can share every position and disagree on every direction, which is a genuinely weird sentence that happens to be true. Here's the thread I want to leave you chewing on. The staircase length was 4. The real answer is pi, about 3.14. The staircase overshot. And with those inscribed polygons, Archimedes came in from below, under the true value. So the honest methods and the lying methods sit on opposite sides of pi, and pi is squeezed in the gap between what points tell you and what directions tell you. Now, the thing that still bugs me. The staircase converges to the circle perfectly. As a set of points, it is the circle in the limit, and yet its length in the limit is 4, not the length of the thing it became. The limit of the shapes has one length, and the limit of the lengths is a different number, and both are completely valid. Those two limits just don't have to agree. They almost never tell you that in school. Anyway, go rewatch the fold, and this time you'll see exactly where it cheats.